Hi, my name is Kate Edwards. I'm Sales and Operations Manager from Outram Research. This is the first of a few training sessions we're putting together to help explain some of the most common power quality parameters and the aspects that the men and women working for distribution network operators on the ground might encounter. This first session is all about flicker. I'll first of all introduce Outram Research for those of you who don't know us. Then I'll explain what flicker is, why it's important, a few of its causes, and then relevance to you. So what standards do you have to adhere to and how do you measure it? Outram Research is a privately owned company based on the south coast of England, which has been designing and manufacturing power quality analyzers using their extensive signal processing experience for the last 30 years. We sell our power quality and fault level monitors to all the major UK DNOs, many industrial customers, and the largest network operators in the US, as well as selling to Australia, New Zealand, Middle East, and more. We focus not only on providing the best equipment for the troubleshooting of power quality, but we pride ourselves on providing friendly, technical, and useful support. Outram has cracked some of the toughest measurements on the market, such as all the individual harmonics to the 100th, as well as interharmonics and subgroups, THDV, THDI, all to the 100th, all of the things that you need, in the UK especially, to show compliance to engineering recommendation G55. But our equipment can also measure the prospective fault level at LV and MV, which before now could only be done by computer modelling, as well as high-resolution frequency measurement to 0.001 Hz resolution, which is needed for National Grid's dynamic containment provision. Today, we're going to talk specifically about flicker. What is it? Well, it's a visible change in brightness of a lamp generally caused by small, low-frequency voltage fluctuations. Those changes are generally not harmful to other bits of electronics, but they can be a nuisance. It can also be early indication of a developing fault. Since we all see it through our own eyes and interpret it with our brains, it's not only subjective, but we are not all affected in the same way. If you suffer from epilepsy, there's something like a 4% risk of flicker causing seizures. If you suffer from migraines, flicker can bring them on. People with eyesight disorders may suffer more than others. Newsreaders always warn us if reports they are about to show contain flash photography. How much it affects us depends on a number of things: how often and how regularly the voltage fluctuates, the frequency with which it fluctuates, and how much of a voltage change occurs, and whether it's a sudden change or a gentle one. Of course, if there's quite good ambient light, you might not notice it even if there was quite bad flicker in the lights above you. It depends on the kind of light. Fluorescent lights, initially thought to be a potential problem, in fact don't respond with as much flicker as, say, tungsten filament lights. LEDs can also cause flicker problems, although new EU regulation has now been put in place to eliminate this. It also depends on the gain factor of the lamp, which is how much of a change in brightness occurs for any given voltage fluctuation. Here's some terminology. You may be familiar with short-term flicker, PST, and long-term flicker, PLT, which are measures used to express irritability. But they start with PU, the unit of perception, and that's how much we perceive flicker to be occurring. A value of 1 is the degree of flicker that about 50% of us will become aware of. It's not irritating, but we will become aware of it. They found these sorts of results by having lots of people in a room and then ran subjective experiments where they changed the flicker frequency, changed the amplitude, and asked them to do certain tasks and then to indicate when they became aware that the lights were flickering. So a unit of perception of 1 is the level at which 50% of people become aware that flicker is taking place. In fact, it's not very different from the point where we become irritated, and PST and PLT are measures of irritation, not so much whether or not we can see flicker at all. A unit of 1 PST is bordering on irritation for 50% of the people. The short-term perceptibility, the PST, is assessed over a 10-minute period. PLT, long-term perceptibility, is assessed over a longer period, 2 hours. If we happen to notice the lights going down as someone plugs a kettle in another room and they just go down once, then you probably wouldn't think anything of it. If it happens frequently, then it becomes irritating, which is why it's dependent on the frequency, and that irritation level is assessed over a period of typically 10 minutes. There are some processes that take much longer, and the cycle of the flicker generation might last for a couple of hours, for example in a steelworks. To accommodate this, the additional parameter long-term perceptibility was introduced, so we have 2 perceptibility measures, short-term and long-term, typically 10 minutes and 2 hours. The bottom figure, instantaneous flicker sensation, is a key parameter in measurement of flicker, and that instantaneous flicker sensation is intended to react as we do. It's a short-term thing. If the lights go down when the kettle goes on, you merely observe it and forget about it again. That instantaneous flicker sensation behaves in exactly the same way. So what sort of numbers are we talking about? This is the PST equals 1 irritation curve. What is it that we're actually susceptible to? Here's a graph of the fluctuation levels that cause irritation to 50% of the people, that red line. Here's the change in the voltage that causes 50% of us to begin to become irritated. And if the number of voltage changes occurring per minute is relatively low, say 1 change per minute, half of us can tolerate about a 3% step in voltage each time without becoming irritated. If we increase the speed of these steps to 10 per minute, 100 per minute, at 1,000 per minute, which is 8.8 Hz, it only takes 0.35% voltage variation for us to become irritated. At 240 volts, that's less than 1 volt variation. We all know our voltage is not that stable. Relatively, it's all over the place. Therefore, it's fortunate that the variations that do occur are not that quick. Otherwise, we'd all be complaining of flicker all the time. So the degree of irritation we experience is very much related to the frequency of the variation that's causing the flicker. And just because a voltage is within tolerance is no guarantee of flicker-free lighting. Above about 25 Hz, we become less sensitive as the separate flickers fuse into something our eyes treat as continuous. We can be affected by higher frequencies if they can match our sensitive region. Okay, so how, in general, is it caused? Well, you know why the voltage goes up and down, line impedance and load variation, and tap changing. But in particular, the causes are typically arc furnaces, induction motors, anything with a high inrush current like that. Arc welders are a good one, spot welders, improperly set processes like a pump on a water site hunting against its levels, they can all generate flicker. We've put in ovens too, as they can cause problems as well. Any electronics that isn't working properly, especially if it's drawing a large load, can cause flicker. Flicker is worse the closer you are to the load, naturally, and if the impedance of the system is high, you have a bigger voltage variation for any given current variation. If you get a big current variation and the system is weak, i.e. the fault level is low, then you'll get a larger voltage variation. The larger loads cause more flicker, and it's made worse, of course, if the lighting that you're under is high gain factor, i.e. a relatively high brightness change for any given voltage change. The jury's out whether dimmers make life worse or not. So what rules are in place for flicker? In Europe in the 80s and 90s, the boffins in their committees went to work generating the first measurement standards and published network limits that you may be familiar with. For example, following all that work, it is now the case that any PQ measurement unit that says it can measure flicker should state that it complies with the requirements of IEC 61000-4-15 and or IEEE 1453, which are the same, apart from various test points, as they encapsulate how it's done, how you measure it, and present the results. Flicker limits were established for different classes of equipment. An EN 5160 was first published in 1995, which included, among other things, flicker and characteristics that were permissible and which were not. Looking at the most recent standards, P28 was introduced, with the latest version being from 2019. This is the study of how the power system responds when loads are suddenly connected or disconnected and the resultant voltage fluctuation. And as I mentioned before, in 2020, the EU introduced a new regulation for LED-based light bulbs to ensure they're flicker-free. EN 5160 was updated in 2022. So looking at EN 5160 first, the only requirement for this standard is to keep PLT to a level of less than or equals to 1. And it's not always the whole measurement, often only the 95th percentile, which means that PLT must be less than or equal to 1 for 95% of the time. Over a week, the PLT can be over 1 for almost 8.5 hours, and you would still be within spec. Compliance to P28 is slightly more stringent. At LV, the PST is allowed to be 1, but the PLT is only 0.8, and these go down as the voltage increases. For a week's recording, the 95th percentile is used, but this goes up to the 99th percentile for shorter measurement periods. So how to make meaningful flicker measurements? You use equipment that can measure short-term and long-term flicker measurements, obviously. But you also want kit that can report flicker sensation and voltage down to really good resolution, single cycle, for example. As you may have gathered, Outram's whole range measures flicker to both IEC 61000-4-15 and IEEE 1453, and can measure that flicker sensation down to single cycle using our adaptive store recording regime. That's from our PM1000, our single-phase monitor, through to the PM2000, a split-phase monitor only available in the US, through to our three-phase offerings including the PM3000, PM7000 and our substation monitors. So how do you set up flicker measurement? Well, with a PM1000, this is the preloaded configuration in all new units, where, as you can see, flicker measurement is already set up and good to go. If you have a different configuration already set up, you can always add flicker to the measurement list, assuming you have available channels. If not, you can swap out something else to make room. You can do this using PM Screen, which is the user interface available either over Bluetooth to an Android phone or tablet with the PM Screen app, or through the Pronto for Windows software with the unit connected to your laptop. It's the same with the default configuration with the PM3000 and, you guessed it, with the PM7000 as well. So once you've got your measurements, you can view them in Pronto like this. This is a recording made with a PM1000, but the software is the same for all of our analyzers, so there's no worrying about whether you have the right version or a dongle. It's the same software for every model, and from here you can create graphs. This is actually a particularly old graph, but it's a relatively good example, which shows the voltage at the bottom and the instantaneous flicker sensation in the middle. You remember a perceived value of 1 is where we become aware flicker is taking place, and anything above that and we rapidly become irritated by it. The edges of the voltage variation here are significant, and we do detect a modest PFS when that happens, but the rate is not sufficient, as in they are not happening frequently enough to cause significant flicker. The PST remains relatively low at 0.3. That shows that we depend very much upon the frequency of the occurrence as to how bad the flicker might be. Our second example is when one of our utilities received a call from a lady complaining that her lights had suddenly started flickering. This was not in an area known for flicker problems, and we understand the utility company were a bit sceptical. They went and monitored for voltage compliance and everything was fine, but the lady still complained. Next time they took one of our loggers with its flicker measurement capability, and when they played the data back through Pronto, this is what they found. The voltage was within limits, but the flicker certainly was excessive. On only 2 occasions during the week did the PST fall below 1. So what was causing this? Was there a clue? It peaked on a Saturday morning, but anything else? Was it self-induced? The utility were inclined to think so, but in fact we do have more information. We have the current graph, and more especially, we have the instantaneous flicker sensation. This is where it's really useful. If we zoom in, this gives us the pattern of the flicker. Here's a 6.5 hour section around Sunday midnight. Burst of activity unrelated to current, which is small, it is midnight, lasts just a few minutes, but is then repeated a few minutes later. Here's one of those bursts shown with the voltage over 2 minutes. Each one is over in a fraction of a second, around 80 milliseconds. So what might have been causing that? Could it be someone extremely busy welding or some machine doing moulding through the night? Could it even be criminal? It turns out that as the utility were digesting this data, the lady phoned up once more rather sheepishly to say it had stopped. So we actually don't know what caused it, so I can't tell you. Although we can see, because of the detail of this data and the fact that you can see that relationship between the flicker sensation and the voltage with no reaction on the current, that its cause is likely to be external to this customer's property, which gives you a good place to start to go and find out what might be causing it. So back to your data and how you can view it. You can create graphs, such as the ones we've just seen, which indicate whether you might have a problem and, importantly, how you might diagnose what's causing it, or tables such as this one, in just a few simple clicks. Now, this is what you need for your standards compliance, the 95th or 99th percentile for PST and PLT. It'll give you that backing when you're talking to your customer, whether it's confirmation that something is wrong and you'll have detailed data in order to help you try to get to the bottom of it, or you can show them that the values you're seeing are below the standards you have to adhere to. If we head over to Pronto, I can show you how that's done. So if we head over to Pronto, we can now show you how to create those graphs and tables. So here I have a project open and we're in the Data Streams tab. We can select or check the box of the parameters that we want to include on our graph. For example, we've got volts here and we've got long-term flicker and short-term flicker. And now all we need to go and find in the functions panel is this graph checked data streams button. And there your graph is immediately produced. We can go and add a title if we want, double click on there and select, type in whatever you'd like. I'll include flicker there. And that's a simple and easy graph to perform, of which you can then zoom in to the relevant detail if you want. Now, if we want to create a table, then all we need to do is essentially the same process, but instead of going to the graph, you can then table using Assistant. So I'll click on that, can create a title for my table, Flickr 95th percentile, and click Next. I then select the parameters that I want to have in my summary table or in my data table. And at this point, I don't actually want the volts in here. I just want the 95th percentile of the PLT and the PST. So we'll click Next. And here's where we select the parameters in the table. So I want the mean of these values over a 10-minute interval. And I can check here, they've got the 2 hours mean and the 10-minute mean. And you can check or uncheck these boxes to give you your options. So I click on Next. Here's where you can choose your summary data. So what we're looking in this table is for that 95th percentile value. So I've checked the mean, the max, the minimum, the times and the max and the minimum if you would like. And I've also checked the upper 95th percentile limit. Now, if I wanted the 99th, I can choose that here, or I can type in whatever percentile I actually want, but the 95th is what we're going to use for now. Then we go and select the time period for your data. So either you can choose a particular session if you have multiple in a project, or you can choose all the data, or you can individually change the timings using these slide bars here. Sometimes if, for example, you've taken a logger off and you've not stopped the recording beforehand, sometimes the voltage goes a bit off the wall, and you may want to take off the last 10 minutes or the first 10 minutes depending on how you hooked it up, but this particular recording is fine. So then we can click Next, and here you can indicate what you'd actually like in your table when it's exported. So you can either have the main data, which includes literally every 10-minute mean value throughout the recording, but that adds a bit of complexity for now, or even just a bit too much detail than we actually need. So I'm just going to select just the summary statistics here and choose that the output is going to be in Pronto format. I can also choose to have it in RTF, which I can then save into Word, or Excel or CSV, various other options. But I'm not going to do that for a moment because I can actually do that later as well. And I'll click Finish. And there you have it. You've got your table of your long-term and your short-term flicker with those all-important 95th percentile values. As you can see, this particular scenario is very, very high flicker. If I want to go and put this data into a report, I can either export to Excel if I'd like, or as I mentioned earlier, export to Word, save it in an appropriate place. That one, I've already got that in my file, but that's fine. And then you can open it and save it into Word should you need to. So here it is. Save it there. I can file save as into Word. Easy. And actually then I can do whatever I like. I can Control-C, Control-V, and drop that into another document. It's all very straightforward. But what the most interesting point is now is actually that you can either open the Table Assistant again to go and amend some of those parameters that you included before if you'd like to, or you can save this table as a template. So I've got various other templates in here as well, but in this situation, the Pronto for Windows software actually saves it in a sensible place. So you want to keep them all in the same place because in order to set up templates, your computer needs to know where to go and find them. So it's useful to keep them all in the same place. So here I have chosen, I'm going to put it in my single phase folder, and I'm going to call it Flickr 95th percentile. Which I in fact have one already, so I will just save over that. And what this means is I can close this down. So this is on one set of data. I can close this down. I can actually open up another example data. And in this case, I can now go and table using a template. And as long as that set of data has the same or the required parameters for my table, this will be highlighted in green here. So these red ones all need harmonics up to the 100th, for example, in their table, so we can't use those. But these particular ones here have got all the data we need. This orange one here has some of the data, but not all of it. So we go and get Flickr, double click on that, and in just 2 clicks, I've created that 95th percentile value for the long-term and the short-term flicker just from a new set of data. And as you can see from this particular recording, they're well below the limits. So mitigation, how do we deal with flicker? It depends on the source of the problem, and the good news is that 90% of the problems are self-induced by the customer. Poor joints, bulbs not screwed in tightly enough, or just unfortunate configurations. So 90% of them are all right. Many problems can be removed by a little thought on routing or by adding an additional feed locally to a fending plant if you can. The not so good news is that 10% are serious. They may be expensive to mitigate, probably caused by heavy industrial sites. The solutions, unfortunately, are not going to be cheap, but I'll leave that in your capable hands. And finally, I hope I've given you some useful insights into flicker to give you a better idea of how and why your customers may be having issues with it, how you can measure it, and what results you can get from our analyzers. I've nominated a basic introduction to harmonic sessions next, although please do get in touch if any of these topics below are of interest. Thank you very much for listening to my flicker explanation. You can find more information on our website at outramresearch.co.uk or email us on sales@outramresearch.co.uk or call us on +44 1243 573 050 and we'll be happy to help.